Alright, this is part 3. So the last video I showed you what happens when you have no electrical resistance. You basically short circuit. So let's continue. So here's a short circuit. Notice the wire here. And then you can see the resistance is futile. You know, it's a common saying, but it's funny now, right? Because you can see the resistor, which is the symbol right here, is useless if this wire is here. So the resistance is futile. Ha ha ha. Very funny, right? Oh boy. Okay, so that's a joke. So resistors are little devices that look kind of like peanuts, right? And they have little bands on the sides, and these bands tell you the value of the resistors. There's a color coordination for each of these bands. Like brown means 1 and the black means 0, so we can actually figure it out. If you do, it's measured in ohms. And again, the Greek symbol for omega right here is our symbol for ohms. So, turns out there's a relationship between current, voltage, and resistance. And some of these might seem pretty obvious. If I add more energy to the system, then the electrons will move faster. So, if I add more voltage, energy, you'll get more current, I. The opposite's true with resistance. If I increase the resistance, well, it's going to be a lot harder for our current to move, so it's going to be less current here. So we can relate that into a mathematical law, which is called Ohm's law. Current is related to the voltage divided by the voltage divided by the resistance. And these are all of our symbols and our values for each of these. So current I in amps, V for voltage, which is also voltage, that's really nice, and R resistance in ohms. So which light is brighter? A 1.5 volt battery, so like a AA or a 9 volt. If you said 9 volt, you are correct. If there's more voltage, there's more current. We can literally prove this. Let's get rid of one of these just for now and do this. Play. So let's do, we're looking at the battery, right? So if I make the battery 1.5 volts, you can see it's moving, not much, but moving, very slow, versus a 9 volt. Oops, 91. Let's try 9. There we go. Regardless, more voltage means more current. And then the opposite's true. Let's make this more current by adding more voltage right here. Let's make it nice and 25. Show value. Of course, you can't really see it, but this says 10. And watch what happens. If I change the resistance to a higher value, let's do 20 instead of 10, boom. You can see that it gets less current. Just like that, just like we predicted. So Ohm's law does work. How about that? And that's basically what this next slide is referring to. So let's calculate some of these values using Ohm's law. Oops. Let's try that again. There you go. Ohm's law says that the current is equal to voltage divided by R. Part A. A hairdryer draws 7.5 amps. That letter A means it's going to be a current. So that's my I. Amps when it's plugged into a 120 volt line, which happens to be the voltage here. So voltage this is actually pretty accurate numbers right here. Just like that. So we have current and we have voltage. The question is, what is resistance? So what is our R? So we can find that out. This is very similar to what we did before, but I equals V over R, where I is 7.5 amps, equals 120 divided by R. And that is our setup. So anytime you have a variable on the bottom of the fraction, you could switch these two. And when you do, it will look like this. This would be the correct setup. And then if I calculate that out, which I'm doing right now, grabbing my calculator, 120 divided by 7.5, I get a nice number of 16. Now the units are ohms. And if you did voltage versus amps, that's also correct. So this is actually true as well. But the more appropriate one will be ohms, just like that. Okay, how much charge Q passes through 15 minutes? Here's a two-parter. Now it's asking about charge and time, so that's going to be the other way we can measure current. Q over T, and it's asking for Q. T, once again, is not in seconds, so I'm going to convert 15 minutes to seconds by multiplying by 60. When I do, I get 900 seconds. I have the appropriate T. I have I, which is from our problem, which is 7.5. So now I can solve for Q. 7.5 is our I, equals Q. Sorry, a little laggy, over T. Oops. Just like that. Oops, sorry. 15, 900 goes here, because that's our time in seconds. 7.5 amps times 900 seconds gives us a lot of charge. So 750 coulombs of charge. And that's part B, and that is part A, like that. So we can use either definition of current to find any of these features. So this is a good two-part problem. You'll definitely see one of these in your test. Questions? Send me an email. You'll see this on your homework as well. So, Ohm's law is a linear relationship. So when you plot I and V on a graph, you'll get a linear line. Pretty cool. These things obey Ohm's law. We could say they're ohmic devices. So things like a resistor is ohmic. Let's write that in there. In my high school classes, we do a lab to prove this. It's pretty cool. Where we, resistor, there we go. It's a terrible spelling, that's okay. We do this, and we actually do get a pretty good straight line when we use a resistor. Of course, that means that there's things that are not ohmic, right? And you can see that it doesn't make that linear line. So another device is called a diode that makes this, but a more relevant one might be like a light bulb. So this will also prove that curve, so same thing in our labs. We actually proved that, which is pretty neat. So the last part of this is I want to talk about circuits in terms of like how to read something like this. Now we won't read anything crazy like this, but I can pick out a few things, and you should be able to pick out a few things and draw a circuit very much like this. Because as you can see, if you looked at a real circuit board, it wouldn't look like this. It looks like that green thing I showed you, maybe more toward the beginning. But it's actually very helpful to draw them as symbols instead. So here are some of the basic symbols that I'm going to show you how to do. So a switch is like a light switch, open. You keep the end here open, and close is when they actually close it like that. A battery is a long and short line where the long line is the positive and then the short line is the negative. A light bulb has a squiggly line inside a circle, like this. A resistor is just a squiggle line. And we won't use a fuse, but it would just be a box, and it would be volts. Voltmeter measures the voltage, and an ammeter measures the amperage. So here's an example, right? So if I want to draw this circuit using just the symbols, it's going to look something like this. So a battery, notice the positive ends here and the negative ends here, would look like this. That's the battery. And then we like to draw it boxy. So the wires are just going to be straight lines. And then I'm going to draw the light bulb. So the way you're going to draw the light bulb is like if you continue the line and then make it stagger like that. I'm going to draw this, and you're going to make it stagger like that. And then finish off the box. And there you have it. That's your circuit design for a light bulb, 2 light bulbs, and a battery. Just like that. And that's a nicer version of that, but you can see I drew that. Try again. Ooh, more complicated. So, same idea. I have to find the positive sides of these batteries, right? So that's all that. And they're all the same direction. So there's 1, 2, 3. I just always draw the batteries first. It's just the way I do it. It doesn't really matter. So I need to draw 2 light bulbs here. So 1, 2. Notice that the squiggles go in line with the wire. And this one, squiggle, like that. Ta-da! It's not pretty, but it is exactly what it's showing. 3 batteries, 3 light bulbs, and it's showing the wire connections of our circuit. And there you have it. Now notice that I didn't put the lines in between. That's totally fine too. I actually prefer the lines in between, a line here and a line here, but this is fine too. So it's pretty cool. Turns out you can do 2 types of circuits, even though you have the same amount of materials. So depending on how you connect your circuit, it's going to be different. So we have 2 types of circuits. One is called a series circuit, one's called a parallel circuit. Now, a series circuit is when the charge only has one path. So this is a one loop kind of circuit. A parallel has multiple paths, so it's going to have 2 types of, sorry, I'm drawing a blank. 2 ways the charge can go. So, here is a visual. So remember that these are batteries right here, and these are light bulbs. Notice in the series circuit, and this is measuring current. So, if you notice in the series circuit, we have 1 loop. So this makes a different type of circuit than this one. This has 1, 2 loops. The charge has a choice. And in the next lecture, I'm going to show you the difference between these 2. So here we go. We'll figure out the brightness between the 2. Which one has more current between the 2? Which one has more, which circuit is brighter? Which lights are brighter? So you can kind of make a prediction now. But I'm going to stop it and then on the next set of slides talk about it.